Welcome to this explainer. Have you ever just looked up at the ceiling and wondered how those little plastic devices actually know what's happening in a room? Well, today we're going to completely demystify that hidden life-saving infrastructure. We're going to map mechanical fire detection directly to how our own human senses work. It's actually really fascinating stuff. So let's dive right in. Here is our roadmap for today. We'll start with the basics of what a fire actually produces, move into how detectors feel heat, see smoke and flames, and even smell gas. Then we'll wrap up with the calculations and the strict positioning rules that tie this whole system together. Section 1. Let's start with the absolute fundamentals of what a fire spits out into a room before it spirals completely out of control. I want you to think about this. If a fire started in the room you're sitting in right now, how would you actually become aware of it? Well, we usually detect threats with our innate human senses, right? We feel radiant heat, we see smoke billowing, we see the flicker of flames, or maybe we smell something burning. Remarkably, electronic fire detectors are engineered to mimic this exact human experience. They are, quite literally, a building's artificial senses. So what are they sensing? A fire produces three primary detectable effects. First, aerosols, which are basically tiny particles suspended right there in the air. Smoke is a prime example of an aerosol. Second, we have vapors. This is that cloudy, diffuse matter often released when materials overheat, right before true combustion even kicks in. And third, gases, which are the direct result of the chemical reactions of combustion. Now, those early smoldering stages produce a ton of gases and microscopic aerosols, making them the very first detectable effects we can target with our electronic senses. Moving right along to Section 2. Now that we know what a fire produces, let's explore our first mechanical method of detection, feeling the heat. Thermal detectors respond to heated air rising via convection. The way this works is often through what's called a bimetallic strip. It's actually a pretty brilliant piece of engineering. Two entirely different metals, like brass and steel, are bonded tightly together. As convection heat rises from a fire, these two metals heat up and expand, but at completely different rates. Because they expand differently, the strip is actually forced to bend. Once it reaches a predetermined temperature, it bends just far enough to make physical contact, completes the electrical circuit, and boom, it triggers the alarm. Now, the crucial thing here is understanding the trade-offs of this specific technology. The massive advantages of thermal detectors are that they are highly reliable and way less prone to those annoying false alarms compared to other sensors. They're basically sturdy little shields. And they're also incredibly cheap to manufacture. But here's the catch. Their distinct disadvantage is that they are slow, kind of like a snail, honestly. The hot air has to physically rise all the way up to the sensor, and the mass of the sensing element has to absorb enough heat to actually trigger. That makes them a pretty bad choice for environments where life-saving early warnings are absolutely critical. Section 3. Let's move on to our next sense and look at how systems actually see smoke, which is usually the earliest visible indicator of a fire. There are a couple of ways to detect smoke, and one of the most fascinating is the ionization smoke detector. It operates in 4 specific steps. Step 1, a battery powers 2 small metal plates called electrodes. Step 2, a tiny, safe amount of radioactive material called americium-241 converts air molecules inside the chamber into positive and negative ions, which creates this continuous electrical current. Step 3, when a fire starts, smoke particles float up, enter the chamber, and literally bond with those ions. And finally, step 4, that bonding breaks the normal path of electricity. When the flow drops, the alarm goes off. If we imagine zooming right in on that third step, it's wild to think about what's actually happening. The dark smoke particles physically enter the chamber and completely interrupt that beautifully organized flow of positive and negative ions bouncing between the plates. It's literally a microscopic interruption, but it's one that saves lives every single day. Alternatively, we have optical or photoelectric detectors. These rely on light and something called the Tyndall effect. In clear air, a beam of light shoots straight across a little chamber, completely missing the sensor. But when smoke enters, those particles act like thousands of tiny mirrors. They scatter that light beam in absolutely every direction. Some of that scattered light inevitably hits the previously dark light sensor, instantly registering the hazard and sounding the alarm. The trade-off here is completely different from heat detectors. Optical smoke detectors, especially aspirating systems that actively suck air into a network of pipes, are incredibly sensitive and fast. Beam detectors can even cover massive unobstructed areas like warehouses, but that very sensitivity makes them way more susceptible to false alarms. Dust, steam, or even a slightly burnt piece of toast in the break room can easily trick the system, which is definitely their primary disadvantage. On to Section 4. Let's see how this builds into our final two sensory technologies, directly seeing the flame and smelling the chemical gas byproducts. Sometimes waiting for smoke to lazily travel all the way up to the ceiling just isn't fast enough. So flame detectors are designed to see the fire directly, but they don't just look for bright light, oh no. They specifically scan the electromagnetic spectrum. They're hunting for specific infrared, or IR, wavelengths, and ultraviolet, or UV wavelengths that are emitted by combustion. Interestingly, they even monitor the visible spectrum for a very specific flame flicker frequency, usually right between 5 to 30 hertz. If the light isn't flickering at that exact specific rate, the detector knows it's probably just a reflection and not a real fire. Now, imagine a massive space, like a subway tunnel or a towering hotel atrium. For spaces like that, we can actually use video systems. This involves taking a standard CCTV video feed and applying some incredibly sophisticated image processing software to it. The software mathematically breaks down the pixels to visually identify the distinct movement and light patterns of flames and smoke. It literally turns standard security cameras into a highly advanced fire detection network. How cool is that? So, comparing our visual and olfactory options, visual flame detection is incredibly fast and can cover huge volumes of space, as long as the flames are directly visible. But what about smelling the fire? Gas detectors can single out incredibly specific threats, like carbon monoxide or hydrocarbons. While they are highly selective and very sensitive, they are undeniably expensive and require constant rigorous calibration and real wrench-turning maintenance to stay accurate over time. Section 5. Now that we understand the hardware behind all these mechanical senses, we have to look at the mathematical logic engineers use to model them in actual building design. There's a massive engineering challenge here. While heat detectors follow relatively straightforward math, modeling the actual fluid dynamics of smoke is notoriously difficult. Honestly, it's like trying to untangle a giant invisible knot. Therefore, relying on light obscuration, which is just measuring how much of a clean light beam is blocked by the smoke, is a much simpler and highly preferred standard for engineers trying to predict exactly when a detector will activate. To calculate this, engineers use the transmittance formula. Transmittance, represented as T, simply equals Ix divided by I0. I0 is just the intensity of light at the beginning of the path in perfectly clear air. Ix is the intensity of that exact same light after it has traveled a specific distance through the smoke. This ratio neatly isolates exactly how much light is lost to the smoke, directly factoring in the unique extinction coefficient of whatever specific fuel happens to be burning in the room. And finally, Section 6. Let's bring this all back into the real world. Because even the most technologically advanced sensor, perfectly calculated mathematically, is completely useless if it's installed in the wrong place. Location is literally everything. When it comes to layout, the rules are incredibly strict. NFPA 72 lays out guidelines for what's called total coverage. And hey, this doesn't just mean sticking a detector in the middle of a ceiling and calling it a day. Total coverage explicitly includes the hidden spaces. We're talking HVAC plenums, vertical elevator shafts, enclosed stairways, and those dark voids above suspended ceilings. Fires often start in the shadows, so our electronic senses absolutely have to be placed there too. There are also hard mathematical limits on exactly how far apart these devices can be. For general areas, the strict spatial limit for smoke detectors is 7.5 meters. That means the spacing between absolutely any point in a protected room and the nearest smoke detector must never, ever exceed 7.5 meters, not even a little bit. But remember how we discussed that heat detectors are inherently sluggish because they rely on rising convection? Well, because of that slower reaction time, their maximum spacing requirement is significantly tighter. To ensure they trigger in time, the absolute maximum distance to a heat detector is strictly capped at 5.3 meters. As we wrap up this explainer, we are left with a pretty stark warning to consider. You see, often, merely meeting minimum local codes only achieves basic operational goals. Things like simply capturing elevators or shutting down HVAC fans to stop smoke circulation. It doesn't necessarily guarantee the blazing fast early warning required to get people out safely. This leaves us with a vital question to ponder. Is the built environment around you actually engineered to detect a fire in time to save lives? Or was it just designed to check a compliance box on an inspector's clipboard? Food for thought. Thanks for joining me today.